Hello everyone. In this video, we are going to talk about two topics in CoppeliaSim. One is how to log the data in a simulation to an external file, in this case a text file, and the second one talking about the solver engines. So if you remember in previous video, I talked about the difference between Lua and Python, because that's something that we see all the time, and I go and say, hey, script threaded and then Lua Python. Another thing we have never talked about are these guys here right next to the run button. These six are the solver engines for CoppeliaSim. So which one should we pick? What are the properties of them? What is the application for each one of them? That is the second thing that I want to talk about. So let's get started. The first thing we want to do is here I put a connect on a revolute joint and I command the revolute joint to spin and show the surrounding, which basically there is nothing here, but that's fine. And the goal is to get the joint angles of this revolute joint, or the connect in this case, and log it to a text file that is in the local drive. So here is the code, very simple. And I'm gonna share this with you on the video description, but basically this is a simple IO, and in this case really the O part of it, the output part of it. So you see I bring in the sim in the initialization, I get the handle of the joint. Now this is the IO part, this is the new part. So I say file equal IO open. So for the input output, I use the command open, I go to my local folder and I create a text file called joint angle. Okay, and in this case, if this file doesn't exist, this one is going to create one. And here is the permission. I say W. Okay, so here I want to write in that file. It's not opening just for reading, it's open for writing. And then in the first line of that file, I would write joint angles for each simulation step. That is going to be the top line. Then in the actuation, you see that I say, hey, get the time of the simulation and then set joint position, joint handle t times 0.2. So I showed you this in one of the previous video. I'm getting the time, I'm multiplying it by the angular velocity omega, and then the joint angle theta equals t times omega, and initial angle is 0. So I set the joint angle, and this command here is going to cause the joint to spin at a constant omega of 0.2 radians per second. This is the actuation part. Now in the sensing part is I get the joint angle using the get command instead of set. I say, hey, give me the joint angle using the sim get joint position. And since this is in radians, I'm going to convert it to degrees by multiplying by 180 and dividing by pi. That comes from the math library. And I get this V. This is, or you can call it omega, right? Or it's not really actually any of them. It's the angle theta. So, but here call it V. You can call it anything you want. And then I go to that file, that handle of the file, and I say column write. You see, so when you want to write, you have to use column write, column read. So this operation is accessible using the column operator, and then say go to that file and write what? In the string format, write time in second. And what is gonna replace here in the middle? It is gonna be this variable here, which is the simulation time plus the simulation time step. Okay, get that and say time equals those many seconds, and then in the right after that, say what? Say, hey, and joint angle, and then here pass that V that you already got from the joint position, and then backslash, and you say, of course, it's in degrees, and then backslash n means go to the next line, right? It's a carriage return. And this F means it's a floating format, and 0.1 and 0.3 means you use 1 decimal or you use 3 decimals in the result of that. So it writes the time, it writes the angle, goes to the next line, and keep repeating. And this one basically closes the file. Remember, like any other software like MATLAB, Python, if you open a file for some kind of task, once your job is done, you have to close the file. Don't leave the file open, okay? That is very critical. So this is the simple code, and now let's see what happens here. So let's go ahead and run. You see it is running, and once we are done, we're gonna click stop, and now look, if we go to the local drive, here we go, joint angles, right? Look here. That's the first line that was written in the initialization or initiation, and that's what it is. Look, this is the time, this is the joint angle, this is the time, this is the joint angle, and you see that it is going up as you see. Okay, so this is what this is about, logging data. Now, the next thing I promised you to talk about are the solver engines in CoppeliaSim. So what are these? Let's talk about them. As I said, there are 6 of them, and I showed you those, so we're going to talk about them. The first one, if you go and look at it, which is the default one, is called Bullet 2.78. There is another Bullet, then ODE, Vortex, Newton, and Mujoko. So what are these? The Bullet 2.8, which is the second one, is ideally the one you want to use. This is what we call a sequential impulse solver. A sequential impulse solver. What is this? What kind of solver is that? These are the solvers that when they want to satisfy the constraints through the iterations, they constantly apply corrective small forces or impulses, okay, which causes corrections in the velocities between pairs of bodies until the constraints are satisfied. And by satisfied, we are really talking about reducing the error. So let's say there are 2 bodies, and these 2 bodies, like one of them is fixed, the other one is pinned down to this fixed member. So let's say here, this is one of them, and the other one is like this pendulum. So this is like pendulum on the cart. And let's say this one is fixed. So here, ideally, at this point, because of the constraint, at this point of the pendulum should not move, right? It's pinned down to the ground. But instead of enforcing it, if this point has a little bit motion, in this iteration, in the next, let's say in this motion, in this iteration, this point, instead of having a 0 velocity, it has some upward velocity, okay? So this is the velocity that it has. Then in the next iteration, it applies a shock to it, a impulse to it downward, and try to force it back to the place it should be and kill the momentum of it and put it back to 0. Okay, so it gradually reduces the constraint errors, so you would never probably get perfect accuracy, you would never probably perfectly satisfy the constraints, but the good thing about it is very fast, and it could be stable for many robotics tasks, so it is a good balance between realism and real-time performance, especially real-time for performance. If you want to really do it fast, this is the way to go. Okay, and realism, it's relatively realistic, but it's not like extremely accurate. So if you want to do some basic simulations, games, stuff like that, this is really good. The 2.78 is like an older version of this, and it has even weaker stabilization and less accurate than this one. And the reason it's kept really is just for legacy compatibility, okay? So it's not really something that you should be using, although you probably seen me use this guy a bunch, because my goal was just teaching you the stuff. But as you can see, from now on, it's better to use Bullet 2.8, or depending on the application, better to use something else. Okay, so you have to pay attention to what is your application, what your application is. The next one that we have is called the ODE. What is the ODE? The ODE and the Vortex, both of them are the same kind of philosophy. Their method is called iterative LCP. What is iterative LCP? What is LCP? So it is from 3 words: linear complementarity problem. Well, what does that mean? So the way this one applies the constraint is very consistent, and it can handle friction and everything very well. And the way it does it by constraint inequalities. So it incorporates them through inequalities. And whenever you are dealing with solving any kind of inequality, they make the solutions of any kind of optimization or any kind of numerical calculations, they make them slow. So the problem with this too is they are slow, but the important thing about them is they are very stable and they are relatively very accurate, especially Vortex. Vortex is, as I said, like the ODE. The only thing about it is a proprietary language as opposed to ODE, which is open source. But this one can give you industrial grade numerical stability and very, very accurate results at, as you can see, the cost of speed. So these two are slow, okay, but very accurate. It's kind of exactly the opposite of those two on the top. Then we have Newton. Newton physics engine is what we call a deterministic engine. What does deterministic means? Deterministic means if you run it twice with identical initial condition, you're going to get identical results throughout the time. So it's not like you run it one time, you get one thing, you run it another time, you get something a little bit different. Like you see with neural networks, right? With ChatGPT, stuff like that. You ask it a question, it gives you one answer. You ask it another time, the exact same question, you get different answer. That's not how this engine works. It's deterministic. It works in continuous time, and the way it enforces the constraint is through Lagrangian multipliers. So it does use Lagrangian method and Lagrangian multipliers and forces the constraint through those. Therefore, it is very accurate and extremely repeatable. The only problem with it, it's sensitive to the step time, okay? And it's quite a bit heavy in terms of computation because you're dealing with Lagrangian multipliers. Finally, we have the MuJoCo physics engine. This is what we call a differentiable constraint-based physics solver. What does this one do? This one work, the way this is working is through continuous time optimization. So it gets the motion through an optimization. So what is the cost function here? The cost function is a global energy function or a constraint violation function or both. And when you solve it, the good thing is the result that you would get are going to be very smooth result and they are differentiable. The good thing about it is very fast, and if you want to do control jobs or so on, it can do very good job, but when it's hard contacts, it could be less realistic. So if we want to summarize it all, I would say this bullet 2.78, you might not even use it anymore, but the bullet 2.83, the one that uses the impulse, this has an improved stability, medium accuracy, and very fast. It can be used for general purpose robotics. The good thing about it is open source. The ODE and Vortex, which both are using the inequalities, the bad thing about them is they are both slow. Their accuracy are medium for ODE, for Vortex is very high. And also for Vortex, the stability is very high, for ODE is high. In terms of application, the ODE is used for contact stability, where the Vortex is used for industrial level realism. And in terms of licensing, ODE is open source, Vortex is proper. That one and MuJoCo are the only proprietary ones. Newton is very stable, high accuracy, moderate speed, deterministic simulations, and it's open source. And MuJoCo, moderate stability. It is very fast. It is continuous time. It's good for reinforcement learning and controls. And again, it's proprietary, okay? So you can see that these are the pros and cons of these 5 or 6 engines. The last thing you might want to solve is, okay, now I have one specific type of robot. I have an articulated arm, I have a mobile arm, I have a humanoid. I'm grasping something, I'm doing reinforcement learning, I want to do a deterministic test, all sorts of things, jobs. Which one of them do you suggest? Because each one of them comes in a rank, right? So you can, for some of them, say, hey, this is the best one, this is the second best one. So if you want to go and rank them, if you have an articulated arm, a manipulator basically, Vortex is your best bet, then Bullet, then ODE. If you have a mobile robot, Bullet is your best bet. If you have a humanoid, ODE, then Mujoko are your best bet. If you have a grasping task, you better work with Vortex, then ODE. If you have reinforcement learning, Mujoko, and then Bullet. And if you have a deterministic testing, Newton. Okay? And you can see that probably why Bullet is like the default, the first one, because it can do lots of different things. Okay? So it's not perfect, but the accuracy of it is medium, stable, is fast, and it's good for general purpose robotics. So now that you have a better idea about the solver engines, the next time you run your CoppeliaSim, you go and pick one of these that you want, and hopefully you can have a more informed decision about picking your solver. Okay, thank you so much for your attention, and I'm gonna see you in the next video.